is the 17th lecture on phasors and their applications in AC circuit analysis. As you recall, in the last lecture, the 16th one, we introduced an artificial concept of phasors, which basically transforms a voltage or a current which is of the form root 2 V cosine of omega t plus theta into a phasor which is represented as capital V e to the power j theta, and then the cosine omega t and root 2 is taken care of by root 2 e to the power j omega t, and we take the real part of this. This is obviously equal to this real part of this, and here, since all currents and voltages in this circuit shall contain this factor, we decided to ignore this, and we also decided to ignore the real part. In other words, if these two are cut out, this will be implied for all voltages and currents, then the quantity that is left is represented by a phasor V with a bar above it, and we call this capital V e to the power j theta, and in the complex plane we represent this by means of a vector whose magnitude is capital V and whose angle from the real axis is theta. If we do this, then obviously this is a transformation from the time domain into the complex number domain, and it has been shown that with the help of phasors, the circuit analysis, steady state circuit analysis or forced response of a circuit to a sinusoidal excitation becomes extremely simple. Let's consider the three basic elements, namely a resistance, an inductance, and a capacitance. A resistance, suppose I excite this by means of a current I which is root 2 I, let's say cosine of omega t, then obviously the corresponding phasor is I bar, which is equal to I e to the power j 0, or angle. I also write this sometimes as I angle 0. All right. Now if this passes through a resistance R, the corresponding voltage phasor VR shall be simply I times R. All right. In other words, the voltage, the actual voltage, you must be able to go back and forth between the time domain and the complex number domain. The actual voltage shall be equal to root 2 I R cosine of omega t. This is equal to, obviously you see, the phase is 0. So there is no phase change between the current and the voltage. It's true in the time domain, it's also true in the transform domain, and the ratio of the voltage phasor to the current phasor is simply equal to R, which we can write as R 0 degrees. All right. Now this is a trivial case. If we take an inductance now and cause the same current I to flow, that is I equal to root 2 I cosine of omega t, which corresponds to the phasor I equal to I angle 0 degree, then you know the voltage across this is given by L di dt, the actual voltage. This will be minus omega L root 2 I sine omega t, and sine omega t can be written as omega L root 2 times omega L I, can be written as cosine of omega t plus pi by 2. Agreed? So if I write this as a phasor, obviously the phasor shall be omega L I VL phasor shall be omega Li. This would be the magnitude and the angle would be pi by 2. Angle would be pi by 2. This is the angle, cosine omega t plus theta. Alright. I can write this as VL, its magnitude, angle, pi by 2. So, in the case of the resistor, if we go back, if we wish to draw a phasor diagram, that is the currents and voltages, then you see the current is in this direction. Let's say this represents the current phasor I, then the voltage phasor is in phase with the current phasor, that is the voltage phasor also has an angle 0. So, the voltage phasor maybe is up to this on different scales. Current and voltage cannot be represented on the same scale. So, this would be VR phasor. On the other hand, if I represent the current voltage relationship in an inductor, the current phasor is this and the voltage phasor is this, and therefore, if the current phasor is along the real axis I, then the voltage phasor shall be along the imaginary axis, shall be along the perpendicular axis, because it leads by an angle of pi by 2. So, the voltage across an inductor, the voltage phasor across an inductor leads the current by an angle of pi by 2. This may be represented as the voltage phasor, where this angle is pi by 2. Alright. With respect to I as the reference, the current as the reference, the voltage phasor across an inductance leads it by an angle of pi by 2. You also notice that the ratio of VL phasor to I phasor, the ratio of the two is simply given by omega L times omega L and angle pi by 2. Now, is that a phasor? No. Is this a phasor? It is not a phasor. A phasor is used to transform a time domain quantity into the complex number domain. Now, corresponding to omega L, there is no time domain quantity. So, this is simply a complex quantity whose magnitude is omega L and angle is pi by 2. What is such a complex quantity? Obviously, it is j times omega L. The magnitude is omega L and the angle is 90 degrees. That is why it is purely imaginary, j times omega L. Alright. And you notice that for an inductor, the voltage and the current, if one of them is sinusoidal, if the current is sinusoidal, no, I am sorry, if the current is exponential, e to the st, then the voltage is SL times e to the st, and SL was defined as the impedance of the inductor. And you see that this quantity of voltage phasor to current phasor, when the excitation is sinusoidal, is simply given by SL with S replaced by j omega, and therefore this can be called as the impedance ZL of the inductor to a sinusoidal excitation of frequency omega. That is, instead of e to the st, what we have is e to the j omega t, and therefore S is replaced by j omega, and j omega L is the impedance of the inductor. To make this explicit, we say ZL of j omega, that is impedance of the inductor at a sinusoidal frequency of omega. That is, S is replaced by j omega. Alright. In that sense, what is the impedance of a resistor? Irrespective of the value of S, whether it is DC or an exponential, truly exponential quantity or a sinusoidal quantity, the impedance is always equal to R and the angle is 0 degree. However, I must caution you, j omega L is not a phasor. It is a complex quantity, j omega L. Alright. It is not a phasor. A phasor is a current or voltage which is a representation of the corresponding quantity in the time domain. It is a transform of a current or voltage. If I now take a capacitor and allow the voltage across the capacitor C to be, let us say, root 2 V cosine omega t, all right, then the corresponding current is C dV dt, and therefore root 2 omega C minus V sine omega t, all right. The current is C dV dt is equal to this, which I can write as root 2 omega C V cosine of omega t plus pi by 2. Why is that?
It's pi by 2 minus omega t. So it is same as omega t minus pi by 2.
This is minus sine omega t can be written as cosine omega t plus pi by 2. Yes. Is that okay? I don't want cosine 90 minus theta, that because that is sine theta, there is no sine change. There is a sine change here, cosine, from cosine to you go to sine, and therefore cosine omega t plus pi by 2. And therefore, if the corresponding phasor quantities are denoted by V, then V phasor is simply V angle 0 degree, and I phasor, I sub C, the current in the capacitor, is simply omega C V angle pi by 2, which indicates, that is V sub no, this is I sub C magnitude angle pi by 2, and therefore in the phasor diagram or the real imaginary or the complex plane diagram, if this is V, if this is the phasor V, all right, then the current leads the voltage phasor by an angle of 90 degrees, and therefore the current, the current would be like this, I sub C phasor, and this angle is pi by 2, all right. So in a capacitor, the current leads the voltage by an angle of 90 degrees. We always take rotation in the anti-clockwise direction as positive. So we say the current leads the voltage by an angle of pi by 2. Correspondingly, in the case of an inductor, the voltage leads the current by an angle of pi by 2. If I take the ratio of voltage phasor to the current phasor, you see that the ratio is simply 1 over omega C angle pi by 2. Now a complex quantity which is omega C, magnitude omega C, and the angle is pi by 2, obviously is a purely imaginary quantity, and therefore its actual representation would be j omega C. And since it is the ratio of a voltage phasor to a current phasor, this is the impedance of the capacitor ZC. All right, this is the impedance of the capacitor ZC. Is that okay? Impedance ZC is not a phasor. All right, it is simply a complex quantity, and you notice that it is quite in tune with the definition of an impedance for e to the st excitation. E to the st excitation, the impedance was 1 by SC, and here S is replaced by j omega, and therefore we say ZC j omega. All right, impedance of the capacitor. If I summarize these relationships, for a resistance, inductance, and a capacitance L, C, R, then the relationships between the current and voltage phasors, it is implied that all excitations, all currents and voltages are of the form cosine omega t plus some constant theta root 2 times a constant. All currents and voltages are of this form. If that is so, then the current in the resistance, well, we can now represent only in terms of phasors. Let's do that. This is IR phasor, and the voltage phasor is VR. This is IL phasor, and the voltage phasor is VL, I sub C phasor and the voltage phasor is VC with this polarity, then the relationships are that VR is simply equal to R times IR phasor, or the other way around, IR is equal to VR divided by R, which I can write as G times VR, where G is the conductance, all right. G is the conductance of the resistor. Similarly, for a inductor, we have VL equal to J omega L IL. J omega L is the impedance of the inductor, or IL is equal to VL divided by J omega L, all right, which indicates that the admittance of an inductor YL is simply equal to J omega 1 by J omega L, that is correct, and its impedance ZL equals to J omega L, all right. For a capacitor V sub C, well it's okay, V sub C would be equal to I sub C multiplied by its impedance, that is by J omega C, is that okay? Or I sub C bar is equal to J omega C VC bar. The impedance of the capacitor is 1 over J omega C and the admittance of the capacitor is J omega C. Whenever a quantity, impedance or admittance is purely imaginary, the real part of that impedance or admittance goes by a special name, and we shall introduce the name here itself. The name is, if there is an impedance which is purely imaginary, let's consider the inductance for example. If ZL is equal to J omega L, then the real part of this is known as reactance. That is, what we do is we write this as J XL, where XL is equal to omega L and is called the reactance of inductance L. Similarly, when we write Y sub C as equal to J omega C, I write this as J BC, okay, J times a real quantity, where B sub C is equal to omega C, and this is called the susceptance of C, susceptance, all right. It's not that we could not write the impedance also. The Z of a capacitor, impedance of a capacitor is 1 over J omega C, which I can write as J times minus 1 by omega C, can we? Yes. Then we write this as J times XC, and XC is called the reactance of the capacitor C. The reactance of a capacitor is negative, the reactance of an inductor is positive. As you see, the reactance of the capacitor is 1 minus 1 by omega C. We can, after we define the impedances for sinusoidal excitations, we can combine them exactly in the same manner that we combined impedances for e to the st excitation or combined resistances. For example, yes.
Suppose we have an impedance of the form A plus JB.
A plus JB.
So then even in this case B will be called the reactance.
That's right. We reserve the symbol B for susceptance. For impedance we will use the symbol capital X, all right, and the real part of the impedance, an impedance can be of this form. where capital R is the real part, corresponds to a resistance, capital X is a reactance, which corresponds to either an inductor or a capacitor or both, a combination of them, that could also form a reactance. We shall come across this in a minute. Okay, now as I said, once we define impedance for sinusoidal excitation, we can combine impedances exactly in the same manner that we did for e to the st excitation. For example, the impedance of this combination Z of j omega would be equal to R plus j omega L plus 1 over j omega C. So you simply sum up the impedances. This you can write as j omega L minus 1 over omega C, and then we shall call this as the resistive part and this as the reactive part. And you see that the reactive part now consists of the combination of an inductor and a capacitor. And because you also notice that the reactance of an inductor is of opposite sign to that of a capacitor, and therefore depending on which is greater, the reactance could be positive. If a reactance is positive, we call it an inductive reactance. On the other hand, if 1 by omega C exceeds omega L, then the reactance would be negative, and then we shall call it a capacitive reactance. Alright, so reactances, impedances, all of them can be combined in exactly the same manner that we combine resistances or impedances to e to the power st excitation. To take another example, suppose we have an inductor L in parallel with a capacitor C, then I can either find the impedance or I can find the admittance. Suppose we find the impedance, then Z of j omega shall be equal to j omega L multiplied by 1 by j omega C, exactly like resistances, j omega L plus 1 over j omega C, which is equal to j omega L divided by omega squared, well, 1 minus omega squared LC. Is that okay? And you see that depending on omega, when omega squared LC is less than 1, the impedance is inductive, that is, the reactance is positive. When omega squared LC is less than 1, then Z j omega is equal to j times a positive quantity, so it behaves like an inductance. On the other hand, for frequencies when omega squared LC is greater than 1, when the reactance is negative and therefore the impedance behaves like that of a capacitor, and when omega squared LC is equal to 1, the two reactances cancel each other and the impedance becomes infinite. What does it mean? It means that no current can flow. At that particular frequency, that is omega equal to 1 by square root LC, omega naught squared LC equal to 1, at this particular frequency, this circuit behaves as an open circuit, and this is called the condition of resonance, as we shall see later. But enough of words, let's see from a picture as to what this lead and lag mean in terms of actual sine waves. Alright, we recall that the current and voltage in a resistor, they are in phase, there is no phase difference. The current in an inductor leads or lags the voltage? Lags the voltage. The current lags, the voltage across an inductor leads the current by an angle of 90 degree, and in a capacitor the opposite happens, that is, the current leads the voltage or voltage lags the current. Let us see what it means in terms of a picture. Is this visible on the monitor? This curve, I will explain one by one. This curve, that is the blue colored curve, this is the current I equal to root 2I cosine omega t plus theta, and the corresponding drop in a resistor VR is simply this current multiplied by R, which I have called I times R, I have called VR, root 2 VR cosine omega t plus theta, and it is this curve. Obviously this and this are in phase, that is the maxima and minima occur together. Whenever the current is a maximum, the voltage is a maximum. Whenever the current is a minimum, the voltage is a minimum, and so on. Alright. On the other hand, this curve, the black one, represents the voltage across an inductor when this current flows through this. And you can see that the voltage leads the current by an angle 90 degrees, which means that on the x-axis here it is omega t, that when omega t is lagging, when 90 degrees ahead of the current, the voltage arrives at a maximum. The voltage reaches a maximum half a period. Is it half or 1 quarter? 1 quarter period. 1 quarter period earlier, which corresponds to a voltage phase advance or phase lead by 90 degrees. So this is what it is. On the other hand, the voltage across a capacitor, if the same current passes, shall lag behind. In other words, it will reach its maximum quarter of a period later. This is what it means in terms of the actual voltages and currents. Is this clear? Omega t is represented in terms of degrees. You see, because root 2I is cosine omega t plus theta, we didn't take omega t, we said omega t plus theta to be completely general, which means that the maximum will be reached at omega t equal to minus theta, and that's what happens. The maximum of the current is reached at omega t equal to minus theta. This difference is theta. And then the maximum of the voltage across the inductor is reached 90 degrees earlier. The maximum of the voltage is reached, voltage across a capacitor is reached 90 degrees later. Is this picture clear? Okay, or are there any questions? I am going to do an example now, alright, to illustrate these points. But before the example, how do KVL and KCL translate in terms of phasors? You know that KVL in general is summation VI equal to 0 around the loop, and KCL is summation Ij equal to 0 at a particular node. Now if each of these voltages is of the same frequency as it would in a linear circuit, it cannot change frequency, alright, then each of these voltages can be represented in terms of its phasor notation. That is, each of these could be represented as real part. I can take the real part outside, root 2 Vi, let us say, e to the power j theta e to the power j omega t. Now this quantity root 2 e to the j omega t would be common to each of these voltages, and the real part would also be common to each of these voltages, and therefore I can get rid of this and I can simply write Vi phasor equal to 0. Is this okay? A very simple argument says that KVL should be valid if we replace the time varying quantities by their transforms, that means phasors. In an exactly similar manner, the KCL translates into Ij phasor, summation Ij phasor equal to 0. Alright, so KVL and KCL can now be translated in terms of phasors. Phasor quantities also obey KVL and KCL. Let us take an example. Suppose we have the line voltage 230 root 2 cosine of, let us say, 100 pi t let this line voltage be applied to a parallel combination of, let us say, a resistance, an inductance and a capacitance. Then, and let us say the values are R, L and C. The resistance, the currents in the three branches, if added together, shall obviously give the current that is supplied by the source. If I represent the currents and voltages, all of them, by phasors, then the corresponding phasor of this would be 230, then e to the power j 0, and therefore the current IR phasor representation would be 230 by R angle 0. The current through the inductor would be 230 divided by, yes, omega L, and the angle would be plus or minus pi by 2. So I can also write this as 230 by j omega L. That angle is taken care of automatically. In a similar manner, the current I sub C phasor shall be equal to 230 times j omega C. That means 230 omega C angle plus pi by 2. And therefore, the total current phasor I, total current phasor I shall be IR plus IL plus I sub C. I can manipulate these quantities algebraically rather than writing out differential equations and solving differential equations. If the excitation is sinusoidal, I can work solely in terms of phasors, and this offers tremendous simplification in in AC circuit analysis. Let us take another example. I have a voltage, now I represent by a phasor. The frequency is unimportant. I represent it by a phasor, a voltage source. I have a resistance and a capacitance. I will do this very slowly. Resistance and a capacitance, and I have an inductor L. The current phasor in this is IL. The current phasor in this is IR. Obviously IR and I sub C shall be the same, right? The same current flows to resistance and capacitance, so it suffices to find IR. It is given that R equal to 2 ohms, L equal to 0.2 Henry, and it is also given that IR, that is the actual current through the resistance, is given by 10 root 2 cosine of 10t plus 45. This is what is given. Alright, is that clear? A voltage source is connected across parallel combination of two branches. One consists of an inductor L, value 0.2 Henry, and the other consists of a resistance and a capacitor in series, resistance 2 ohms, the capacitor is not known. Alright. The question is, on a phasor diagram, show IR and VR. On a phasor diagram, show IR and VR and draw an arrow to show the direction of the voltage across the capacitor, that is V sub C. Alright, this is first part of the question. Now that is obviously very simple. IR as you can see, the current phasor would be simply equal to 10 angle 45, and the voltage phasor VR shall be equal to 10 times 2, that is 20 angle 45. This is volts and this is amperes. Alright, so the phasor diagram would be take a vector 45 degree at an angle of 45 degree and you represent, let us say, this length by, for the vector IR, you take different scales and you represent this a vector in the same direction as VR as the voltage across the resistance. Alright. Now this length is 20 and this length is 10. This is in volts, that is in amperes. We are showing the direction is the same but we have different scales. Okay. The next question is, show the direction of VC. Now obviously VC,
Excuse me, sir.
yeah,
VR will be smaller than IR.
there are different scales. Okay. We choose to have a smaller scale for VR. Alright. Now the current, the voltage phasor across the capacitor, obviously this will be IR divided by J omega C, which means that it is IR by omega C and angle is minus pi by 2. Minus pi by 2 with reference to whom? With reference to the IR vector, and therefore it goes like this. This is the direction of VC. Is that clear? The capacitor voltage shall lag the current by 90 degrees and therefore this angle must be 45. Is that okay?
Minus 40.
This angle is minus 45. Okay. The absolute value of the angle is 45. The point is that VC lags IC by 90 degrees. So this part of the question is fine. The next part says, next part is interesting. If the voltage phasor, that is V, you recall V is the exciting voltage. Let me draw this circuit again. Okay. If V is V 0 degree, sorry, then show V and VC on the diagram and determine V of t. Alright, let us pose the question like this, that our original vector diagram was like this. I had a VR in this direction and a VC was perpendicular to it. VC direction was this. Let me show the direction. This is the direction of VC. Alright. Now it is said that V, which is the sum of VR and VC, has an angle of 0 and therefore V is in this direction. Is that clear? V is in this direction, and then what does it specify about VC? VC is equal to? Say it again. The magnitude of the magnitude shall be equal, and therefore if I measure this, this would be my VC, such that when I complete the parallelogram will now be a rectangle, isn't that right, or a square? It will be a square because this is 45, this is 45, and therefore this is my voltage phasor. You are now required to find out VT. Pardon me? How do you find VT? Obviously this angle is 45, so cosine 45, it's an interesting question. Cosine 45 would be base divided by hypotenuse. So VR divided by V. Alright. Therefore VR is equal to, well, V equal to VR divided by root 2. No. It's the other way around. V would be equal to root 2 VR. V would be equal to root 2 VR. That's right. And therefore, what is VT then? VT is simply Yes? Come on. IR
40 cos 10 t
40 cosine 10t. That's all. Because the angle is 0. Angle is 0. Alright? You see, why did this come? Because small VR was 20 root 2 cosine of 10t plus 45. That's what it was. Alright? The magnitude of the phasor V, the magnitude of the phasor V is root 2 times VR. So root 2 times this will be 20 root 2 multiplied by root 2, which is 40. And the angle is 0, so it simply ends at cosine 10t. Is that clear? Huh? Okay, please. What we have seen is that our original equations, let's say 10 root 2 cosine of 10t plus 45. So what is VR then? VR is 20 root 2, because R is 2 ohms, 20 root 2 multiplied by cosine 10t plus 45. And therefore the phasor VR is equal to 20 angle 45. We have seen that the magnitude of V, I want to find the phasor V, the magnitude of V is equal to root 2 times VR, which means that magnitude of V is 20 root 2 and the angle of V is 0 degree. Therefore, the corresponding Vt must be root 2 times the magnitude, the RMS value, which is 20 root 2 multiplied by cosine of omega t plus whatever the angle is 0. Is that clear? And therefore, this is what we get. You recall that root 2 I cosine omega t plus theta corresponds to a phasor which is I angle theta. It's the other way around. Now we have to find V angle 0 degree. What is the corresponding Vt? So we multiply V by root 2 to get the amplitude and cosine of omega t plus the angle, which is 0. And omega is 10. Omega is 10. And therefore this is the result. Where did I write it? This is 40 cosine of omega t. Alright? We will do more examples to illustrate this. Take another example. Let's say we have a V. We shall make a changeover from time domain quantities to complex domain quantities and vice versa again and again. You must have been noticing that the small case letters I reserve for time and capital letters for phasors. Okay. So there is a current I, there is a voltage V, and the circuit consists of R equal to 2 ohms and then an inductance L equal to 1 Henry and a capacitance C equal to 0.05 farad, and the output voltage is taken here, V sub C. These are time domain quantities, and now we specify that V of t, let's say, is 5 root 2 cosine of 5t. Alright? You are required to find out V sub c. You are required to find out V sub c. And in the process, you are also required to find out a complete vector diagram, complete phasor diagram. That is, I want to know what the current through this resistance is, what is its phasor. I want to know what is this current, let's say IL, IR, and IL is equal to IC. Then I want to know what is the relationship between IL and VC in terms of phasors, and finally I want to know what V sub C is. All right. Now I also want to know what this current small I is, what is the corresponding phasor, and what relationship does it bear to the phasor small v. Let's proceed systematically. First of all, the phasor representation of this would be V equals to 5 angle 0. Okay, this is the phasor representation. If I want to find out I, if that is my only concern, then what I do is I find out the impedance. All right. Now instead of impedance, obviously it is easier to find the admittance because things are in parallel. So let's find out y j omega, and we will get very interesting results. Y j omega obviously is half plus admittance of this, which is 1 by r, plus 1 by impedance of this plus this. So it would be j omega L minus 1 by omega C. Is that okay? J omega L is the impedance of the inductor in series with the impedance of the capacitor minus j by omega C. All right. Let's substitute the values and see what happens. You see, omega is 5. All right. And L and C are given, and therefore y of j omega is equal to half plus 1 over j. Omega is 5 and L is 1, so 5 into 1 minus 1 over 5 into 0.05. So this is equal to half plus 1 over j, 5 minus 4. So this is simply half minus j. All right. 5 times 0.05 is 0.25. 1 by 0.25 is 4. Okay. So this is the admittance. Then what is this current phasor I? This would be the admittance y j omega multiplied by the voltage phasor V. All right. The current phasor is admittance multiplied by the voltage phasor V. So this is equal to half minus j times what is V? 5 angle 0 degree. And therefore what is the magnitude of this? I can write this as 5 by 2, or I can simply write this as 5 half minus j. Angle 0 degree does not contribute anything, and therefore what is its magnitude? It is 5 square root of half plus 1. Is it okay? 1 quarter plus 1. All right. And the angle is minus tan inverse, not pi by 2, tan inverse imaginary by real, so tan inverse 2 minus tan inverse 2. Is that okay? Now if I simplify this, the current phasor is equal to 5 square root 5 divided by 2. Is that okay? Okay. And then minus tan inverse 2. Oh, I don't know how much minus tan inverse 2 is. Minus tan inverse 1 is 45.
Must be around 65.
Well, whatever it is, you look at the phasor diagram now. This is my V.
63.5.
63.5, all right. Minus 63.5. And what is 5 root 5 by 2? 2.5 is about 31. No, it's less than this. How much? 2.5, about 5.6, okay. Alright, so the current phasor therefore lags the voltage by an angle of, it's not to scale, 63.5, and the current phasor is here. If that's what I want, if that's the only thing that I want, alright, and the corresponding current quantity I of t, the corresponding current would be given by, yes, can you tell me what will be the current? Root 2 times, that is 5 square root of 5 by 2, is that okay? Root 2 times this, alright, then cosine of 5t minus 63.5, this will be the current. I didn't manipulate anything, I simply manipulated some complex quantities, alright. Now suppose instead of this, I want to find out the current through the resistance. Let's get back to the circuit. This is the circuit. What is IR? IR is simply V, small v by R, and therefore the IR phasor would be equal to 2.5 angle 0 degree. Alright. Suppose I want to find out IL. That would be more interesting. Now look at, yeah. Pardon me? The phasor IL. What do you think its relationship shall be to the voltage phasor V? I should be happy if you can say. Pardon me? V by J XL plus XC, which can be either positive or negative. What does this mean? It means that the current may lag by 90 degrees or by 270 degrees. Isn't it right? Yes. 180 plus 90. We shall continue this next time.